We will continue with our 24th lecture in this course on process control, analysis, design and assessment. So, in the last few lectures we have been talking about control of time delay systems, talked about what time delay means, why is it relevant in practical situations, the difficulties that come because we have a time delay term in the transfer function which takes the transfer function away from the ratio of polynomials form, and we talked about how we can control such systems, and we introduced the notion that you actively use the model in the controller implementation also, and that allows us to control these time delay systems effectively. At the end of the last lecture, I also left with a question as to how we are going to look at the stability of these systems now that we know how to think about controller design, implementation for a given performance metric. The next question is, once you have designed a controller based on performance, since we are giving up a little bit of performance and so on, we have to also look at whether the designs are stable, when will it become unstable and so on. This is particularly important because while we will have a G desired which by design would be stable. So, for the nominal system, that is if the model and the process have the same transfer function, the closed loop system is going to be stable. However, the real challenge is to really think about what happens when my process is different from my model. So, will the stability idea still hold, and we will see how to analyze stability of systems with. Now, the reason why we need a new idea, and which is what I am going to introduce in this lecture called Nyquist stability criterion, is because whatever we have been looking at till now is not useful anymore for time delay systems, mainly because we have this e power minus tau ds term in the denominator. And once I expand this as polynomial, I can expand it like an infinite polynomial. So, conceptually I have infinite poles, which will be difficult to handle either in a partial fraction approach or Routh stability table. So, we need to come up with some other idea, and that idea that is used is what is called Nyquist stability criterion. This is pretty sophisticated mathematical idea at an undergrad level for engineers. So, what I am going to do is I am going to explain the basic fundamentals behind this idea without showing you proofs or getting into very complicated mathematics. Okay. So, I am going to basically make you understand the result of Nyquist stability more than actually trying to show you why the result is true. So, to do that, we have to think a little bit about complex variables and how they behave, and we have to think about a little bit of mapping from one plane to another and so on. So, let me start by explaining the key ideas behind Nyquist stability criterion, and what we are going to do is I am going to generally explain this idea using simple systems which are still polynomial by polynomial form to get you to the basic idea, and then we can look at how this is useful for studying time delay systems. Okay. Till now we have always been talking about a transfer function. It could be g of s, or as we have written here, f of s, and a transfer function has poles and zeros, and if we take a transfer function of this form, then we say that this transfer function has m poles and m zeros and n poles. Now, at the beginning of this series of lectures, we asked what is s, and then I said s is a complex variable which can take some values. Now, we are going to expand on that idea and then explain Nyquist stability result with that. The result that I am going to show is based on two other results. One is called the Residue Theorem and the other one is principle of arguments in complex analysis. We are not going to go into either of these ideas in any detail at all. What is more important is for us to understand how to use these ideas in stability analysis for control systems. So, the very first idea that I want to explain is the following. So, think about this just like a function, right. So, if you let us say if I give you f of x, let us say is x squared plus 3, let us say is a function that I give you, and then I asked you what is the value of f of x at x equal to 0, then you will say f of x is 0 squared plus 3, okay, it is 3. So, f of x is 3 when x equal to 0. right. So, you can think of this f of s or any transfer function also in a similar way, and basically you can evaluate the transfer function at any value that I give. So, for example, think of f of s just like f of x, but now it is a function of a complex variable, and if I want to evaluate f of s at let us say s star, then basically you are going to say f of s star is, instead of s you are going to substitute this value s star minus z1 all the way up to s star minus zm divided by s star minus p1 all the way up to s star minus pn. The only difference is, if I want to explain this, let us say in a plot, all I would need is basically one 2D plot. By this what I mean is, I could plot this x on the x axis and f of x on the y axis, and I am done. So, for example, x equal to 0 is a point where f of x is 3. So, this is a point on the curve at x equal to 0, f of x is 3. Now, if I set x equal to 1, then f of 1 is 1 squared plus 3, which is 1 plus 3 4. So, at 1 this will be let us say 4, and at 2 this will be 2 squared plus 3, so 7, and so on. So, you can draw this picture whichever way it turns out, something like this. So, all I need is one 2D picture f of x versus x, and I am done with this, right. So, this is how I represent this. Now, if I were to think about plotting this in a similar way, I cannot just do with one plot. Okay. The reason is the following. Number one, the argument here x has only one value. Of course, from a complex number viewpoint, s has a value, but that s has a real part and an imaginary part. So, this itself, this x itself, when it becomes s, needs two axes to represent a variable. So, if I told you s equal to let us say 2 plus 3i, then to represent this s itself I need two axes. So, this is the real axis and this is the imaginary axis, and this says real part is 2, imaginary part is 3. So, this will be 2 plus 3i. So, notice the difference here. When I look at x f of x, very simply I can look at a 2D plot and be able to plot this, whereas the minute I come to s, basically I need a plane or a 2D plot to plot s itself. So, this plot of s, the different values that I can let s take itself is called an s plane. Okay. So, this is something that is important to remember. So, think about the transition from here to here. Now, what happens to f of s, right. So, here if I put a value x, I get one value f of x. So, that is the reason why I could just do it with two axes here. However, s itself has become an s plane, and when I substitute a value for s into this equation, then I am going to get f of s, which is going to be a scalar. However, this f of s is going to be a complex number again, because s is complex, z1 could be complex, p1 could be complex, and all of those. So, f of s itself is a complex number. So, it would require, so for example, if I put s equal to s star and this turned out to be some f real plus I f imaginary, this is the complex number value it turns out to be, then to plot that I need another plane, which is what I am going to call as fs plane. So, this is a very important first concept that you should remember. So, if I want to find what the f of x value is for an x, I go all the way up here and then simply read out, and then that gives me the f of x value. But if I have to pick a value here and then I say what is f of s, then I have to go back to this plane and then say okay, this is f of s. So, this is a difference when we come to complex numbers. So, this is the first important idea that you should understand, and the reason why we need these two planes is because s is a complex number and f of s is also a complex number. Now, if I let us take another example here. Let us say if I have a function f of x equal to x squared minus 4, then if I want to find out where f of x equal to 0, then I will write x squared minus 4 equal to 0, x is equal to plus or minus 2. Okay. So, when I want to find a particular function where it goes to 0, then I correspondingly solve this and then I will get a value. For example, this is a different function, not this x squared minus 4. So, I will say plus 2 and minus 2 are values at which this function goes to 0. Okay. And those could be plotted in this axis itself. However, if you ask the same question in terms of f of s plane, which is of importance to us from control viewpoint, and we ask the question when will f of s, which is a numerator by denominator, be such that, or in other words, what are the points of zeros of f of s and poles of f of s, which basically will translate to asking the question, just like how I put f of x is 0, asking the question when will n of s go to 0 and when will d of s go to 0. The points at which n of s goes to 0 are called the zeros of the transfer function, and points at which d of s goes to 0 are called the poles of the transfer function. So, just like how I put f of x equal to 0, if I put n of s equal to 0, then the solution would be n of s will go to 0 at s equal to z1, z2, z3 all the way up to zm. So, there are m points at which n of s will go to 0. Notice something interesting. So, in this plot, if I found out where f of x goes to 0, I can plot the x on this line, but whenever I find the zeros of this transfer function, that is, this transfer function is written in the ns over ds form, and the zeros of the transfer function means I am asking when will ns go to 0, those points cannot be plotted here, those points will have to be plotted in this plane. So, basically this single line has become a plane and this single line has become a plane. So, if I ask for numerator going to 0, then the corresponding points are plotted here. Okay. So, if I look at this plot and then say, okay, if I am plotting this, then I might plot this as a 0 point, this as a 0 point and so on. So, you see that plotted in the s plane. So, the key idea is that the zeros of f of s, which are values where n of s goes to 0, will have to be plotted in the s plane, not in the fs plane. So, that is an important thing to remember. Just like here, if you say f of x is 0, then you will find the value where f of x goes to 0, x on the x axis. Now, this axis, since it has become a plane, and this axis it has become a plane, so I look for those in the s plane. Similarly, if I ask where are the poles of this transfer function f of s, then that basically means I have to set ds equal to 0, and those again are going to be values that s takes such that d of s goes to 0, and those again will have to be plotted in the s plane, not the f of s plane. So, this is an important thing to remember. These are all simple ideas, but since you might be seeing this for the first time, I just wanted you to get a feel for how we go from simple real number functions like this and then go on to complex functions. And the key idea is that the argument itself I need a plane to describe, which is a complex number, and the resultant is also a complex number, and I need another plane to describe that. One is called the s plane, another one is called the fs plane, and I could ask questions about the fs transfer function and put the results in the s plane. So, that is what I just explained. If I ask for what are the zeros of f of s, that means the numerator polynomial equal to 0. So, the s values at which the numerator goes to 0 will have to be plotted in the s plane. And if I ask what are the poles of the transfer function, those are the values at which d of s goes to 0, and those values again will have to be plotted in the s plane. So, here is an example where I have f of s which has 2 poles and 2 zeros in the s plane. So, this will be the s plane, and we have not even plotted the f of s plane. So, this is the first and important idea that you have to remember when we discuss Nyquist stability criterion, that is going to come subsequently. So, why are we doing all of this? Just to give you a context for doing all of this. So, basically what we want to do is we want to find out the stability of GC by 1 plus GC, which is this. Though it is not in the polynomial form because I have this e power minus tau ds term in the denominator, I am still going to look for how to understand the stability of this, and basically in some sense I am going to use this for f of s and start thinking about the stability. So, ultimately once I teach in the polynomial form, I am going to say the same results hold even if you have time delay elements in your transfer function, and basically we will replace this f of s by g c by 1 plus g c, and then we will be able to study the stability of time delay systems. That is the thing that we are going to look at. Now that we have understood the ideas of S plane and f of S plane, what we are going to do next is we are going to look at how we identify how many poles or zeros are there in some locations in the S plane by looking at a combination of this S plane and F plane diagrams is what we are going to do. So, in the next lecture I will describe how this is done, and then this I will do for very simple example, so that you understand the basic ideas, and then I will describe how this translates to thinking about control of closed loop transfer functions. Remember, our problem is still guaranteeing that there are no poles in the RHP for a time delay system. So, how some of these ideas translate to the real problem that we want to solve, I will also describe in the next lecture. Thank you.